Welcome to qnawire.
Hi, there is a straight conductor in this given problem and a loop. This is the loop. The direction of current in this straight conductor is upward, and the time rate of change of current is di by dt. With this rate, the current is changing in this conductor. So, due to this change of current, the magnetic field around this conductor will also be changing. So, the same magnetic field will change through this loop also. So, as the magnetic field linked through this loop will change, so the magnetic flux linked through this loop will also change, which will give rise to an EMF induced across this loop and a current induced in this loop. So, first of all, the distances of the arms of the loop from this straight conductor are given as, here this is the distance A of this first arm, and the second arm is at a distance of B. Then we consider a thin strip in this loop. This is the thin strip having a width dr. This is the small width of this strip having a magnitude dr, and we consider this strip to be at a distance of r from this straight current carrying conductor. The length of this loop, rectangular loop, is given as L. Now, if the conductor is A, B, in the first part of the problem, we have to find at an instant when the current is I, at an instant the current is constant as I. So, we have to find the magnetic field B at a distance r to the right of the wire. Means at the place of this strip we have to find an expression for the magnetic field, and we know this expression for the magnetic field using Biot and Savart's law. Biot and Savart's law, this magnetic field in vector form, if we say at the place of this thin strip, is given by mu naught by 4 pi into 2I by r in a direction inward, perpendicular to the plane of paper. Using right hand screw rule. So, this is the answer for the first part of the problem. Now, in the second part of the problem, we have to find the flux, the small flux through the narrow shaded strip. So, this small flux will come out to be the magnetic field B, which we just found in the first part, the magnitude of this magnetic field B into the area of this thin strip dA. So, the area of the strip will be length into width, where length is L and width is dr. So, this is the answer for the second part of the problem, and this is the small magnetic flux. So, when we put the value of this magnetic field found in the first part, this expression for the magnetic field comes out to be mu naught divided by 4 pi into 2I by r L dr. This, or if we cut this 2 with the 4, so we will get, this is mu naught by 2 pi into IL dr by r. So, this is the answer for the second part of the problem. Now, in the third part of the problem, we have to find the total flux linked through this loop, for which we will have to integrate this expression of d by b. The limits of the distance r from initial distance a to final distance b. So here it becomes integration of mu naught divided by 2 pi I into L divided by r dr, having limits of r from a to b. Here variable is only r, all other things being constant will be taken out. So it will become mu naught divided by 2 pi I L integration of 1 by r dr from a to b. So this integration comes out to be mu naught by 2 pi I into L integration of 1 by r dr comes out to be natural logarithm of this r, having limits from a to b. So it becomes mu naught by 2 pi I into L. When we put the values of this variable r, so first of all, this is natural logarithm of b minus this is a natural logarithm of a. So when we use the rule of logarithm, this natural logarithm of b minus natural logarithm of a comes out to be natural logarithm of b divided by a. So finally, this flux comes out to be mu naught divided by 2 pi I L natural logarithm of b divided by a. This is the answer for the third part of the problem. Now finally, in the fourth part of the problem, we have to find the induced EMF in the loop, and using Faraday's laws of electromagnetic induction, we know this EMF in magnitude, this EMF is given as differentiation of this flux, the total flux phi b. So d phi b by dt. So if I differentiate this flux d by dt, I put the value of this flux, which was mu naught by 2 pi I L, natural logarithm of the ratio of b with the a. Here in this expression, only I means current is variable, all other things being constant are taken out. So it becomes mu naught by 2 pi I is variable, it will not come out. So this is L times of natural logarithm of b by a multiplied by di by dt. So this is the expression for the EMF induced. Now, in next part of the problem, we have to find the numerical value of this induced EMF when the values of the given constants are, for A, this is 12.0 centimeter. For B, this is 36.0 centimeter. For L, this is 24.0 centimeter. And for di by dt, this is 9.60 ampere per second. So when we put these values here in the expression for EMF induced, we get this is 2 into 10 raised to the power minus 7 for mu naught by 2 pi. This is the value of this constant, mu naught by 2 pi, 2 into 10 raised to the power minus 7. Then for length, we have got this 24 centimeter or 24 into 10 raised to the power minus 2 meter. Then natural logarithm of b by a means 36 centimeter divided by 12 centimeter. So centimeter will be cancelled, and finally multiplied by di by dt, which was 9.6 ampere per second. So when we solve this completely, we get 5.1 into 10 raised to the power minus 7 volt. This is the numerical value of EMF induced, and the answer for the last part of the problem. Thank you.